Hi kiddos, we're going to look at some limit stuff. We had some kind of a station thing set up. We didn't get to do the movement for stations because we have a large class. But as far as each of the individual topics, I'll try to go through each of the problems on here so we can get some help as far as understanding what's going on. First off, we got some limits involving factoring. I'm going to do each of these two different ways if appropriate. The first is to factor and the second is to use L'Hopital's rule, which is the new thing we talked about in class. In terms of the first one, I can see pretty quickly the bottom's going to be 0. And if I plug into the top, we get 9 plus 3 is 12, minus 12 is 0. So we get 0 over 0. That means that the limit might exist, so I'm going to try factoring. So we got the limit as x approaches negative 3. And the top is going to factor into x plus 3. And also x minus 4. A little bit of a pro tip here. If you see an x plus 3 in the bottom, and we get 0 over 0, one of the factors on top is definitely going to be x plus 3. So you only have to figure out what the other factor is. For those of you for whom factoring is really a challenge, this can be a place to kind of save some space. All right, those cancel, and we got negative 3 minus 4 is negative 7. From this point, if you had wanted to instead use L'Hopital's rule, which if we have this indeterminate form, 0 over 0, what we do is we take the derivative of the top and the derivative of the bottom. Sorry, I put negative 3. So that would be 2x minus 1. On the bottom is going to be 1. If I plug negative 3 in, I get negative 6 minus 1, which is negative 7. For number 2, first things first, again, if I plug in 1, I get 0 over 0. That means I might be able to factor. So the limit as x approaches 1 of negative, and then x minus 1 on top. Bottom is difference of squares. That's going to be x minus 1 and x plus 1. Those cancel out. Leave me with 1 on top, and I'm left with negative 1 over 1 plus 1 is 2. If I wanted to instead use L'Hopital's, this would be the limit as x approaches 1. The derivative of the top is going to be 1. The derivative of the bottom is going to be 2x. And if we plug in 1, we get negative a half. I don't recommend that. I think factoring is easier, but I'm trying to give as many examples of L'Hopital's as I can. For number 3, again, just if I plug stuff in, I get 0 on top. 9 minus 3 minus 6 is going to be 0 on the bottom. All right, factoring the top, we can take a 2 out, and that would give me x squared minus 9. So that would end up factoring into, I'm going to write my limit first, just so I make sure I keep my math nice and good. Good sentences I make. So we get 2x minus 3, x plus 3 based on difference of squares. And then on the bottom, that's going to be x plus 3 and x minus 2. Those cancel. And when I plug in negative 3, we get 2 times negative 6 over negative 3 minus 2 is negative 5. So that's going to be negative 12 over 5. If instead, from this point, I've decided 0 over 0, I want to L'Hopital it, we end up with the limit as x approaches negative 3. And for the top, that would be 4x. For the bottom, it would be 2x plus 1. That's going to be negative 12 on top, and negative 6 plus 1 is negative 5 on the bottom. That should be negative over there. I just forgot it. All right, next up, if you're not taking AP credit, you can kind of ignore this section in terms of the math you got to do. For Station 2, these are all going to be conjugate limits. You could also do these with L'Hopital's, but it would come out messier, although if this is a real problem for you, L'Hopital's may be the best way to do this. Okay, first part. I get 0 over 0 if I plug in. I'm going to multiply by the conjugate, which is the square root of x minus 2, and then plus 1 over the square root of x minus 2 plus 1. The way that we talked about this way back in the beginning of the year was we're going to multiply out the top with distribution, and the bottom we're just going to leave unmultiplied. Whatever we're trying to get rid of, we multiply out. Whatever we're not, we just leave alone, because there's probably going to be stuff that cancels all nice for us. So when we do this, the top, we got x minus 2 in square root times x minus 2 in square root, which is x minus 2. The reason that we do this is we were going to have plus 1 and minus 1 the square root, which makes that part go away. And then we're going to have minus 1 times plus 1, which is minus 1. This gives me x minus 3, which reduces. And when I plug the 3 in, we get 1 over 1 minus 2 in the square root. And when I'm plugging in 1, that should be a 3. 3 minus 2 in the square root. Square root is 1. 1 plus 1 is 2. Okay. Number 2, we're doing the same thing. Square root of x plus 8. And then minus, plus 3 on top, and then square root of x plus 8, and then plus 3 on the bottom. When we do this out, again, the bottom is just going to stay the same, so we have the limit as x approaches 1, and the bottom is going to be x minus 1, square root of x plus 8 plus 3. And on top, we're going to end up with x plus 8. The middle parts cancel out. And then we have minus 9, which is x minus 1. We're left with 1 over this part. When I plug 1 in, square root of 9 is 2 plus 3. Sorry, square root of 9 is not 2, it's 3. 3 plus 3 is going to be 6, so we get 1 over 6. All right, and finally, for the third one, we've got 0 over 0 when I plug in. So we're going to do square root of x and then minus 3, square root of x, and sorry, this would be plus 3, and then plus 3. On top, since we're not getting rid of anything yet, I'm not going to multiply those out. And that gives me x minus 9, and then square root x plus 3. On the bottom, when I do that multiplication, we're going to have x and minus 9, hopefully unsurprisingly. Those cancel. When I plug 9 in, we get square root of 9 is 3, plus 3 is 6. And again, if you wanted to L'Hopital's, this is actually not a bad one to talk about that for. You get the limit as x approaches 9. On top, we're just going to have 1. On the bottom, and here's where this gets a little bit tricky, the square root of x has a derivative of 1 over 2 square roots of x. When I plug 9 in, we get this as 1 over 2 square roots of 9 is going to be 6, and that's going to be 6. So you end up in fraction land, which may not be comfortable for you, but you avoid having to deal with conjugates. Same for the third part in terms of if you're honors credit, you don't need to worry about this. If you're AP credit, you should know how to do this. And we could potentially do this with L'Hopital's as well, although these are, again, a little bit on the messier side in order to do that. First thing I'm going to do is to figure out that I have something going on that's weird here. And what I'm going to do is multiply the entire thing by a denominator when I get there, but it might be nice if I found a way to combine those bottom pieces. So let's kind of break this off. 1 over 2 plus x minus 1 over 2. To find common denominator, I'm going to multiply this by 2 plus x and 2 plus x, and this by 2 and by 2. All right, so that gives us on top, 2 minus 2, oh, I'm doing really good writing today, 2 minus 2 plus x, and the bottom 2 times 2 plus x. On top, that would just give us a negative x, and on the bottom, that would give us 4 plus 2x. And as a reminder, this is just the bottom of this fraction. So we've still got the limit as x approaches negative 2 of x, and we're dividing by this, so I'm going to write this as multiply by 4 plus 2x over negative x. That gives us a negative 1, and when I plug in a negative 2, we end up with 4 plus 2 times negative 4, which is 0. Kind of a weird limit for a lot of work. Okay, looking at the second one, I'm going to use a different method for this one. Instead of finding common denominators, I'm also going to kind of shove this one off to the side. What I'm going to do is to multiply the top and bottom by the denominators to get rid of things. So I'd be looking at the limit as x approaches 0, and on top we're going to have x. I'm going to multiply by this denominator on the top and the bottom. So it's negative 1 plus x. And in the bottom, I'm going to multiply each piece by that, so I'm really going to distribute that to both parts. I'm going to get negative 1 plus x over negative 1 plus x plus negative 1 plus x times 1. All right. On top, that's going to give us the limit as x approaches 0, and that's going to be negative x plus x squared. I'm thinking maybe I should not have actually done that out, because I think I'm going to divide by an x on the bottom. This part's going to be 1. So we get 1 plus negative 1 plus x. Those cancel. I can divide everything by an x, giving me the limit as x approaches 0 of negative 1 plus x, which is negative 1. I find this method a little bit easier to work with than finding common denominators and dividing. But you got to be more comfortable in your algebra to do this. And you may or may not be there. I don't know. I can't speak for you with that regards. I'm going to do the same thing for the last one, although you might notice it's the same thing as our first one, but flipped. So my prediction is that if we're flipping 0, we end up with dividing by 0, which is undefined. I don't think this one's going to exist. But let's just try it out. And what we're going to do is do the same method I did this time. So that's the limit as x approaches 0. I'm going to multiply by both of these denominators this time, top and bottom. So we'll do the bottom first, just so we can have that. And we got x times 2 plus x times 2. And then the top of this is going to be 2 plus x on the bottom. I don't know why I'm just not zooming in so I can actually write this. And then on top, that would be 2 plus x times 2. I'm multiplying by both denominators. And then minus on the bottom, we got 2. And then 2 plus x times 2. We got some stuff to cancel out. And we end up on top. 2 minus 2 is going to be 0, and then minus x. And on the bottom, we got all this junk. We got x, and then 2 plus x, and then times 2. Okay, so if I plug in 0, because the limit as x approaches 0. Oh, by the way, those x's cancel out. We've got 2 plus 0 is 2, and then times 2 is 4, so negative 1 over 4. That was not what I was expecting, but hey, that works. Oh, the reason for me being surprised is because we were not plugging in 0 before we were plugging in negative 2. That makes me feel better. Okay, moving onward. Next up, we got to find some limits if they exist. We talked about potentially doing this using graphing, and then we introduced L'Hopital's rule. Because if I plug in 0, I get 0 over 0. So when we take a look at this, we can apply L'Hopital's rule. And that tells us that we can use the derivative of the top and the derivative of the bottom and take the same limit. So the limit is x approaches 0. And by the way, this is not the math notation that you need for the AP test. You need to be more cautious there in kind of an annoying way that we'll talk about later. Derivative of tangent is going to be secant squared of x. Derivative of 3x is going to be 3. When I plug in 0, secant is going to be the reciprocal of cosine. And I know that cosine of 0 is 1. 1 over 1 would be 1. Okay, so this is going to be 1 over 3. And we are very happy to get an answer. For the second one, which we did in class twice, depending on the day that you were there, we also get 0 over 0. And if you're curious, this is the notation. You have to say that the limit as x approaches 0 of sine of 5x is equal to 0, that the limit as x approaches 0 of x is 0. They don't like you writing 0 over 0 as an equal statement. That's the issue there. Therefore, we can use L'Hopital's rule. So then we're taking the limit as x approaches 0 of the derivative of sine of 5x, which is cosine of 5x, and then we have to do chain rule, so that's times 5. The bottom part of this, the derivative of x, is 1. Plugging in 0, we get cosine 5 times 0 is 0, times 5 over 1, which is just 5. For the third one, this one's going to be kind of fun. We're going to get 0 over 0 again. So we're going to use L'Hopital's rule. And we end up getting the limit as x approaches 0 of 6x over sine of 3x times 3. That's the chain rule there. And if you plug in 0, you get 0 over 0 again. So we're going to use L'Hopital's rule a second time. And we get the limit as x approaches 0 of 6 over cosine of 3x times 3 is 9. When I plug in 0, we get 6 over 1 times 9, which is 2/3. For number 4, we have a beautiful problem that's going to involve some delightful L'Hopitaling in a second, because we're going to get 0 over 0 again. I'm going to do L'Hopital's rule, and this time we've got to do some product rules. So I'm going to write the limit as x approaches 0. I'm so excited about this. I do have a way we could simplify this, but it involves knowing some trig that I don't necessarily know that we actually know. So we're going to pretend that we don't know that. I'll do that as a second route through this. And if you remember that, you're like, oh my God, that's amazing. That's fine. Okay, so we got a product. We got first and second going on here. So we've got sine of 3x times the derivative of the first, which is going to be cosine of 4x times 4. We got plus, and then we got the first, sine of 4x times the derivative of sine, which is cosine of 3x, and then times 3. And then on the bottom, we have another product rule, the second, sine of 2x times the derivative of the first, which is 1. And then plus, we've got x times cosine of 2x times 2. I'm going to start by trying to plug in 0 and see what happens, because I'm better off that way. Although I think we're going to end badly here. Sine of 0 is 0, so that whole term becomes 0. Sine of 0 is 0, so that whole term becomes 0. And we end up with zeros on top, and then we got 0 plus, and then 0 on the bottom. We still have 0 over 0. I'm not going to do a second product rule for this in terms of that, because we'd end up with like 3,000 billion pieces, which is maybe a bit of exaggeration. I am going to briefly say something about this, though, that sine of 2 times an angle, let's call that b, is equal to 2 sine of the angle cosine of the angle. So if we've got sine of 4x, that's going to be 2 sine of 2x cosine of 2x if I cut that in half. And the reason that I think this might be interesting is because now I've got stuff that I can cancel out a little bit of. So sine of 2x cancels out on the top and on the bottom. Still not an ideal looking problem, but now you might notice that if I take the limit as x approaches 0, we have 0 over 0, but now if we L'Hopital, the bottom is just going to be 1. And that's a much more palatable thing for us. So the top would end up being 2 times sine of 3x times negative sine of 2x times 2, and then plus 2 cosine of 2x times cosine of 3x times 3. When we plug 0 in, this whole first part is going to be 0. That's going to be 1. That's going to be 1. 2 times 1 times 1 times 3. We end up with 6 over 1, which is going to be 6. Ooh, that was kind of a beast of a problem. And by kind of, I mean that was a beast of a problem. Okay, we've got some piecewise stuff going on here. We're going to start from the beginning. The limit as x approaches -1 from the left. That's using this stem because we're on the left side -1. It's going to be 2a times -1 minus 5, which is -2a minus 5. From the right side, we're going to use this stem. We're going to have 2 times -1 plus b, which is -2 plus b. The limit as x approaches 3 from the left, we're going to use this side, is going to be 2 times 3 plus b, which is 6 plus b. The limit as x approaches 3 from the right side, we're going to use this one, is going to be 4a. No x's to plug in. All right, f of -1, because that has the equals part, we're using this. So that would be -2 plus b. F of 3, since this has the equals part, we're going to use this. And that would be 6 plus b. If the limit as x approaches -1 and the limit as x approaches 3 both exist, what are some values of a and b? So what that really is telling us is that if the limit as x approaches -1 exists, that these first two things have to be equal. -2a minus 5 must equal -2 plus b. For 3, the next two things must be equal. 6 plus b, I'm so glad those are the two numbers and letters that we're using, those don't look the same at all, is equal to 4a. Instead of doing some kind of crazy math that I tend to be prone to, I might just minus 6 from both sides to get b by itself and plug it in. So we get -2a minus 5 is equal to -2 plus 4a minus 6. I'm going to bring this to this side, so we get 6a, -5 plus 6 is 1, plus 2 is 3, a is equal to 1/2. Okay, I'm going to use this equation because that looks nicer, and if we got a is equal to 1/2, that means 4a is equal to 2, so if b is 2 minus 6, b is equal to -4 to make this true. Then finally we got some graphing stuff, although I am just realizing this is part 1 of 3 of this first video. So we got to use this graph to evaluate each question to see if this answer exists. All right, so the limit is x approaches 0 from the left. I want to look at what the height of the graph is doing as we're going from the left to an x value of 0. I'm coming to a height of 0. It does not matter that we have a point up above. All that matters is what we are approaching. From the right side, so we're doing the same thing from the right, and we're approaching 0 from the right side. Since these two are equal, that means that this limit does exist, and it's equal to 0. Ooh, I just put a check mark for something. I don't know what that did. For the next part, we're approaching 1 from the left. Okay, so 1 is here. We're approaching this from the left side. We also get to a height of 0. From the right side, we also get to a height of 0. It does not matter that we have a point outside of this. Limits do not care about the actual value, only what we are approaching. And when we get there, we also have a, I don't know why I said 1 there. That should be 0. We will also reach 0. So both sides equal 0, therefore we get a limit value of 0. 2 from the left. 0 again. 2 from the right is going to be 0.649. In this case, we have a different value from the left and the right, and because of that, the limit does not exist.